Right now, tonight, if you walk outside and look up at the constellation Orion, you will see a faintly reddish star glowing in the upper left corner of the hunter's shoulder. It is not hard to spot. People have been looking at it for thousands of years. Ancient Egyptians knew it. Arab astronomers named it. Medieval sailors navigated by it. And for most of recorded history, it sat there quietly, doing what stars do, burning. But in 2026, everything we thought we knew about that star changed. Hubble, the most famous telescope ever built, has been watching it closely for nearly 8 years. And what it finally confirmed, combined with the most powerful ground-based telescopes on Earth, has stunned every astronomer who saw the data. That star is not dying alone. It has a hidden companion. And together, they are giving scientists the closest front row seat to a slow-motion stellar explosion that anyone in human history has ever witnessed. If you want to understand what is actually happening up there right now, stay right here. Hit subscribe because this channel covers exactly this kind of thing every single week, and you do not want to miss what comes next. The star in question is Betelgeuse. And to understand why what Hubble just confirmed is so extraordinary, you first need to understand what Betelgeuse actually is, because most people have no idea how enormous and how strange this object truly is. Betelgeuse is classified as a red supergiant, which is the largest category of star that exists in the known universe. When astronomers measure its diameter and compare it to our own sun, the numbers become almost impossible to hold in your mind. Betelgeuse is approximately 764 times wider than the sun. But here is the comparison that really makes that land. If you remove the sun from the center of our solar system right now and put Betelgeuse in its place, the surface of Betelgeuse would not just cover our sun, it would not just swallow Mercury, it would not just engulf Venus, it would not just consume Earth and Mars, it would extend past all 4 of those rocky inner planets and push out into the asteroid belt, swallowing Jupiter in some size estimates and leaving only Saturn and the outer planets outside its surface. One single star, sitting where our entire inner solar system currently sits, burning hot enough to be visible with the naked eye from 650 light years away. That is Betelgeuse, and it is dying. The dying part is not news. Astronomers have known for a long time that Betelgeuse is in the final phase of its stellar life. A red supergiant is what happens when a massive star runs low on hydrogen fuel in its core. The core contracts and heats up, the outer layers expand enormously, and the star swells to hundreds of times its original size. It becomes cooler at the surface, which is why it glows red rather than white or blue. And at some point, when the core finally runs completely out of fuel and can no longer support itself against its own gravity, the whole thing collapses inward in a fraction of a second, and then rebounds outward in the most violent explosion the universe produces, a supernova. When Betelgeuse goes supernova, it will be visible from Earth during the day, it will likely outshine a full moon, it will be bright enough to cast shadows at night for weeks. The last time a supernova was visible to the naked eye from Earth was in 1987, and that one was in a galaxy outside our own. Before that, you have to go back to the year 1604, 4 centuries ago, to find a supernova close enough to truly stun the observers who saw it. When Betelgeuse eventually explodes, it will be the single most spectacular astronomical event in recorded human history. The question that has haunted astronomers for decades is simple: when? And for years, the evidence kept pointing in a direction that made scientists genuinely uneasy. Betelgeuse was dimming and brightening in strange ways. It was ejecting huge amounts of material from its surface. Its atmosphere was behaving in ways that did not fit the simple model of a single aging star quietly burning through its final fuel reserves. Some researchers began suggesting the timeline for the explosion could be shorter than previously thought. Some estimates pointed to decades rather than thousands of years. Then, in late 2019 and early 2020, Betelgeuse did something that made global headlines. It dimmed dramatically. Its brightness dropped by roughly 1 full magnitude, falling to levels that had never been recorded in modern astronomical history. Social media erupted. News articles around the world asked the same question: is Betelgeuse about to explode? Astronomers scrambled to analyze the data, and the answer that came back was not what anyone expected. It was not dying. Not yet. It had done something else entirely, something that had never been directly observed in a star at this scale before. It had ejected a massive chunk of its own surface, a cloud of hot plasma the size of a small planet, which then cooled in space and formed a temporary dust cloud that blocked its light from reaching Earth. Betelgeuse had essentially sneezed, a titanic, never-before-seen convulsion that sent billions of tons of stellar material flying into the surrounding space. And then it started recovering. That event, the Great Dimming, as astronomers came to call it, left a puzzle. Why did it happen? What caused a star this size to suddenly throw off a piece of its own surface? And why was Betelgeuse showing such unusual brightness patterns in the first place? For decades, astronomers had measured that Betelgeuse dims and brightens on several different rhythmic schedules simultaneously, roughly 180 days, roughly 230 days, roughly 420 days, and then a much longer, slower cycle of approximately 2,100 days, about 5.7 to 6 years. 3 of those cycles made sense. They matched the known physics of a large star, pulsating, swelling, and shrinking, breathing in and out the way dying stars do. But that longest cycle, the roughly 6-year variation in brightness, did not fit. It did not match any known pulsation model for a single star of Betelgeuse's type. Something else was driving it. And for years, nobody could figure out what. Then, in 2025, the answer arrived. And it came from a direction nobody had fully anticipated. 2 separate research teams, working independently, arrived at the same conclusion at almost exactly the same time. Betelgeuse is not alone. It has a companion, a second star, orbiting around the red supergiant on a roughly 6-year cycle, close enough to actually be passing through the outer layers of Betelgeuse's enormous extended atmosphere as it completes each orbit. The researchers gave this companion a name honoring the Arabic roots of Betelgeuse itself. Betelgeuse's name comes from Arabic words meaning the hand of Al-Jawza, a female figure in Arabian astronomical legend. So the companion was named Siwarha, the Arabic word for her bracelet. That poetic naming turned out to perfectly capture what Siwarha does. It orbits its massive companion like a bracelet around a wrist, circling every 2,100 days. And its gravitational presence leaves a trail of evidence in Betelgeuse's behavior that researchers had been seeing for years without understanding what was causing it. The confirmation came in January 2026 when NASA announced that Hubble Space Telescope data, combined with observations from the Fred Lawrence Whipple Observatory and the Roque de los Muchachos Observatory, had delivered the clearest evidence yet that Siwarha is real and that its effect on Betelgeuse is visible and measurable. The researchers, led by scientists at the Center for Astrophysics at Harvard and Smithsonian, used nearly 8 years of continuous Hubble observations. 8 years of watching Betelgeuse's chromosphere, its deep atmosphere, react to something orbiting inside it. And what they found was described this way by the research team. Think of a boat moving through water. The boat creates a wake behind it, a trail of disturbed water that radiates outward from the path the boat traveled. Siwarha does exactly the same thing as it moves through Betelgeuse's vast outer atmosphere. It generates a dense wake of gas, a trail of material that has been pushed and stirred and compressed by the companion's gravitational influence. And that wake expands outward from Betelgeuse's atmosphere in a pattern that repeats every time Siwarha completes another orbit. That repeating pattern is what Hubble detected, not just once, not just as a hint, but clearly, consistently, over nearly 8 years of data. The wake shows up in the spectrum of light coming from Betelgeuse. When scientists analyze a star's light through a spectrograph, they can see the specific colors produced by different chemical elements in the star's atmosphere. Changes in those colors, shifts in the precise wavelengths of light from specific elements, reveal how the gas in the atmosphere is moving. What Hubble and the ground-based telescopes detected was a repeating pattern of spectral changes, disturbances in the motion of gas in Betelgeuse's outer atmosphere, that line up perfectly with the orbit of Siwarha. Approximately every 2,100 days, shortly after Siwarha passes in front of Betelgeuse from Earth's perspective, the wake becomes visible in the data. It appears, it expands, it fades as Siwarha moves to the far side of Betelgeuse, and then roughly 6 years later it appears again. The pattern has repeated at least twice across the 8 years of Hubble data that researchers analyzed. Lead researcher Andrea Dupree of the Harvard-Smithsonian Center for Astrophysics summarized the discovery this way: finding the wake from its companion means we can now understand how stars like this evolve, shed material, and eventually explode as supernovae. What does Siwarha actually look like? It is not a monster like Betelgeuse. It is a relatively modest star by cosmic standards, a hot blue-white main sequence star with somewhere between 1.4 and about 2 to 3 solar masses, depending on which measurement technique the research team applied. In visual terms, if our sun is a beach ball, Siwarha is roughly the same size or slightly larger, while Betelgeuse would need to be a sphere the size of a large sports stadium sitting next to that beach ball to represent the true scale difference. Siwarha orbits at a distance of about 4 astronomical units from Betelgeuse, which means it sits at roughly the distance that Jupiter sits from our own sun. But because Betelgeuse is so impossibly large, that distance is not actually very far from the surface of the red supergiant. Siwarha is not orbiting at a safer move. It is orbiting partly inside the extended outer atmosphere of Betelgeuse, which stretches far beyond what you would call the visual surface of the star. Every orbit, Sawara plunges through that outer atmosphere, stirring up gas, generating its wake, and leaving evidence of its passage that Hubble has now confirmed is clearly detectable across multiple orbital cycles. Then, in July 2026, just weeks before the time of writing, astronomers delivered the next piece of this story. Using the Very Large Telescope in Chile, one of the most powerful optical telescope systems on Earth, researchers directly imaged a candidate companion at the predicted location of Sawara. The image was published in the journal Astronomy and Astrophysics in late July 2026. The companion appeared at exactly the spot where orbital mechanics said it should appear, based on the timing models built from Hubble's data and the earlier Gemini North observations. The direct imaging confirmation has not yet been independently verified by a second observation because Sawara has now moved back to the far side of Betelgeuse from our perspective and will not be in a favorable viewing position again until November 2027. The telescope time for that observation has already been awarded to the research team. But the current evidence, spanning 8 years of Hubble atmospheric wake detection, prior brightness pattern analysis from 2 independent teams, the Gemini North marginal detection in 2025, and now the Very Large Telescope direct imaging candidate in 2026, has been described by astronomy and astrophysics as the strongest evidence yet that Betelgeuse is truly a binary system. One prominent researcher, who has studied the star for years, said in response to the imaging result, "I find it incredible that we still discover something as fundamental as its binarity in 2026. So what does the existence of Sawara change about the future of Betelgeuse? This is where things get both fascinating and somewhat sobering, depending on whether you were hoping for an imminent cosmic fireworks show. The mystery of Betelgeuse's 2,100-day brightness cycle is now explained. It is Sawara. The companion stirs Betelgeuse's atmosphere during each orbit, creating variations in brightness that had puzzled astronomers for decades. And with that explanation comes a revised understanding of what stage of life Betelgeuse is actually in. The unusual brightness patterns that some researchers had interpreted as signs of a star rushing toward its final collapse now have a different and more stable explanation. Current models, updated with the binary companion factored in, place Betelgeuse in what is called a stable helium burning phase. After a massive star exhausts the hydrogen fuel in its core, it begins burning helium. That phase can last a long time, and with Sawara's gravitational influence now factored into the calculations, estimates for when Betelgeuse will finally explode have been pushed significantly outward. The current scientific consensus places the supernova anywhere from tens of thousands to about 100,000 years in the future. The companion star changed the timeline dramatically. There's also an extraordinary subplot buried inside this discovery. What happens to Sawara when Betelgeuse eventually does go supernova? The answer is almost certainly immediate destruction. When the core of Betelgeuse collapses in a fraction of a second, the resulting explosion will release more energy in that moment than our sun will release across its entire 10 billion year life. A shockwave of unimaginable force will travel outward through the expanding stellar material at speeds measured in fractions of the speed of light. Sawara, orbiting closely inside the outer atmosphere, will be consumed and destroyed almost instantly in the fireball. It will not survive. Before that happens, though, tidal interactions between the two stars are expected to slowly pull Sawara inward over time. Researchers believe that within approximately 10,000 years, long before Betelgeuse ever reaches its supernova, the companion may be swallowed entirely. Betelgeuse may consume its companion star first. And that engulfment event, whenever it comes, will itself be an astronomical event without any known parallel in recorded human observation. The discovery also has implications far beyond the Betelgeuse system specifically. One of the persistent mysteries in stellar astronomy is called the red supergiant problem. Theory predicts that massive red supergiants should be the most common type of star to explode as core collapse supernovae, the specific type of supernova produced when a star runs out of nuclear fuel. But when astronomers go back through historical records and look at stars that were present before known supernovae exploded, they keep finding something strange. Many of the pre-explosion stars do not look like the red supergiants that theory predicts. And in some cases, like a discovery confirmed in February 2026, a massive star 2.5 million light-years away simply vanished without the bright supernova explosion that should have accompanied a stellar death at that mass. It apparently collapsed directly into a black hole, shedding its outer layers in what one research summary described as a slow-motion cosmic fade-out with no dramatic explosion at all. The existence of companion stars, hidden and previously unknown, may be a critical missing piece in explaining why the red supergiant problem exists. If many massive dying stars actually have close companions that are shaping their late-stage behavior, influencing their mass loss, altering their rotational angular momentum, or even being swallowed before the final collapse, Then the predicted appearance of a pre-supernova star and its actual observed behavior may differ in ways that explain the discrepancy. Andrea Dupre put the broader scientific significance directly, with Betelgeuse giving us a front-row seat to watch how a giant star changes over time. Finding the wake from its companion means astronomers can now understand how stars like this evolve, shed material, and eventually explode as supernovae. Other red supergiants that show similar long and short brightness cycles may also have hidden companions that have never been detected, she added. Betelgeuse may be the clearest example of a pattern that is actually widespread among massive dying stars, one that astronomers simply could not see before because they were not looking for it. Now they are looking. And in the years ahead, with Hubble still operating and the next generation of extremely large ground-based telescopes coming online, researchers expect to find companions around other massive stars that were previously thought to be single systems slowly burning alone. There's also something genuinely awe-inspiring about the timing dimension of this story that is worth sitting with for a moment. The light from Betelgeuse that Hubble and ground-based telescopes are analyzing right now left that star approximately 650 years ago. When the most ancient light in the current Hubble dataset departed Betelgeuse, it was the year 1376. The first complete version of Geoffrey Chaucer's Canterbury Tales had not yet been written. The printing press had not been invented. European explorers had not yet reached the Americas. That is, the light Hubble is measuring. And in that light, already 650 years old by the time it arrives at our instruments, scientists can read the wake of a companion star, detect disturbances in an atmosphere spanning hundreds of millions of miles, and reconstruct the orbital dynamics of a binary system that the human species had no idea existed until last year. The telescope is not just pointing at space. It is reading a message that was sent before the Renaissance, carrying information that just arrived. For the next major piece of this story, the calendar is already marked. November 2027 is when Sawarha is predicted to be at its widest apparent separation from Betelgeuse as seen from Earth. That is the next great observing opportunity. Multiple research teams are already awarded telescope time. The Very Large Telescope, the Gemini North Telescope, and very likely Hubble itself will all be pointed at Orion's shoulder at that moment, waiting to capture the clearest possible image of Sawarha in a configuration where its light can be distinguished most cleanly from the overwhelming brightness of Betelgeuse itself. If those 2027 observations confirm what the 2024 and 2025 detections suggested, and what the 2026 Very Large Telescope imaging showed, the binary nature of Betelgeuse will be established beyond any remaining doubt. In the scientific program of studying how two stars, this different in size, interact over time, approach each other, exchange material, and eventually end their shared existence in the most energetic explosion the universe can produce, we'll have decades of work ahead of it. The most famous dying star in the night sky just got considerably more interesting. Tonight, if you step outside and find Orion, look at that reddish glow at the hunter's shoulder one more time. What you're seeing is not just a dying star. You are looking at a binary system, a giant swollen red supergiant, so enormous it would swallow everything from our sun out to the asteroid belt, slowly losing mass, pulsating, stirring its own outer atmosphere as an invisible companion orbits every 6 years through its outermost layers. Two objects locked together in a gravitational relationship that will eventually end in an explosion bright enough to be seen in daylight from Earth. Nobody alive today will see that explosion. But every time Hubble turns its instruments toward Betelgeuse, we get a little closer to understanding exactly how it will happen, why it happens, and what it tells us about the lives of the largest stars the universe is capable of building. The slow-motion explosion has already begun, spread across thousands of years of stellar dying. And for the first time in human history, we have the tools to watch it happen in real time.